Robert Fathauer. I have a small business called Tessellations that includes a online store called mathartfun.com and a polyhedral dice brand called the Dice Lab that's in collaboration with Henry Segerman. Today I'll talk about logarithmic spiral tilings of triangles. Before I launch into that, I'm just going to show some recent sculpture. These are all hand-built ceramics. This one is Mobius band with 3 half twists. And the second one here is a trefoil knot. It looks different in different angles, so. And what's next? This is a part of an infinite weave based on something Rena Schroloff showed on social media. It's basically a periodic version of the Borromean rings that's made using 3 different clay bodies. This is in this year's art exhibit. It's kind of a hyperbolic exponential growth form. It's just kind of done by hand, not calculated, and then some texture was added. This is something called a hyperbolic helicoid. Royce Nelson provided a 3D graphic I used to guide the construction of this piece. And I think that's it for those. Okay. Let's make sure we're on the same page as far as terminology goes. It's a little hard to define what a spiral tiling is, but we're going to use a working definition saying it's a tiling emanating along a spiral curve from a fixed point, whereby the tiles located further away from the point are larger. So each triangle here is called a tile. A straight line segment of one of those is an edge of the tile. This is a corner of the tile. Where 3 tiles or more meet, it's called a vertex. And all these diagrams should be understood to be infinite tilings. So it continues ad infinitum, excuse me, both outward and inward. And there is a point in the center it approaches called the singular point, where the tiles get infinitesimally small. So there's some well-known examples of this kind of thing. The best known is the golden spiral. Martin talked about this in some depth. And as he also alluded to, you can write down equations by comparing distances. So 1 is equal to s plus s squared, where s is a scaling factor between 0 and 1. That gives you this equation, and the solution for s is the golden mean, 0.618 ... This is kind of the equilateral triangle analog of that, not as well known. I first saw this in a talk by John Sharp at Bridges many years ago. In this case, you scale 5 times, 1, 2, 3, 4, 5, until you share partially an edge with the starting triangle. So now our equation is 1 equals s plus s to the 5th, which is harder to solve, but these days you just use an online equation solver. Like Wolfram Alpha, this is just a free website. You type in your equation, it equals, it gives you real solutions and imaginary solutions. Of course, you want the real solution between 0 and 1, which in this case is the plastic number, or the inverse of the plastic number. Here's another one that's been known for a while. This is a golden spiral of triangles. Each triangle is golden. The ratio of edge lengths are golden, and the scaling factor is golden as well. And that's about it for the particular type of tiling I'm going to talk about, at least for triangle ones. There's various rectangle ones. Let me first make a distinction between tiling or spiral types. This is the Archimedean spiral, where the arms are spaced at a constant distance. And this is an exponential spiral, logarithmic spiral. In the case of tilings, all the tiles will be the same size, be congruent here. And here they would increase by a linear scaling factor. This is what an Archimedean spiral tiling looks like. You can see this kind of figure in Greenbaum and Shepard, for example, been known for quite a while. So here we start with a radial tiling of triangles, and we just shift that by one tile and get a two-armed spiral. So I'm not going to talk about this type of spiral tiling any further. So what I'm going to do is derive a general expression for this sort of spiral tiling. We have a single spiral, the tiles are not arranged in edge-to-edge fashion, and to try to develop equations you can use to generate a variety of these. So our starting triangle we're going to label, sides are A, B, and C. I said equal to 1, and opposing angles are capital A, B, and C. So we're going to shrink that by S and rotate it and position it so that the base is against the side like so, showing a corner. And as we go around, when we get to the nth triangle, we partially share an edge with the starting triangle. So we can now write 1 is equal to BS plus AS to the n. So that's our first equation. And for the next one, note that this triangle rotates as it scales. When you get back to here, it's rotated most of the way around. And if you just rotate it this much more, which is the angle B, it'll be back to the starting orientation, from which we can write NA plus B equals 360 degrees. And those are really the two equations we need. So we're going to use the fact that B equals 180 degrees minus A minus C to write A in this form. And now to make it a tiling, we're going to choose N and C and use that to calculate A and calculate B. Then we're going to use the law of sines to calculate little a and little b, and then plug this into an equation solver to get the value for the scaling factor. You then have all the parameters you need to draw an accurate spiral tiling. As the concrete example, the one shown here, n equals 5, 1, 2, 3, 4, 5. C is 80 degrees, A and B are 65 and 35, and the scaling factor is about 88%. So let's look at some special cases first. Isosceles triangles, two of the sides are equal. There are three ways you could arrange two isosceles triangles. You can go side to side, side to base, or base to side. Looking at side to side first, the equation simplified because B equals C, and it turns out there's a single solution for a given n, and there is a solution for any n greater than 2. The first one is that golden spiral of triangles. That's the second one. Third one is the equilateral plastic number spiral, and they keep going. I should mention that Cy Waldman first demonstrated this in 2016 for this side-to-side case. Next, the side to base case. In this case, A equals B, and a tiling is allowed for any n greater than 3. I skipped 5 because 5 again is the equilateral triangle case. Here's 4, 6, and 7. And moving on to the last isosceles case, that's base to side. Again, a tiling is allowed for any n greater than 4. Again, I skipped the first one, which is the n equals 5 equilateral triangle. So these are 6, 7, and 8. So you can generate a wide variety of tilings using isosceles triangles. Another special case is right triangles. And there are, again, three ways to arrange these. In this case, it's leg to hypotenuse, hypotenuse to leg, and leg to opposing leg. It turns out there are no solutions allowed for this configuration. For the other two, though, starting with leg to hypotenuse, in this case, the angle C is 90 degrees. So again, there's a single solution for each n, starting with n equals 5. Note the angles here. For angle A is 67.5, 54, 45, and 38.57. If we go to the other case, the hypotenuse to leg case, we find the same triangles for the same numbers of n, but the way they fit together is different. So it gets quite a different appearance with the same set of triangles. Again, that's to leg hypotenuse, and that's the hypotenuse to leg. So 90 degrees is not special, and really what I've shown so far implies there's a continuum of allowed tilings for any n. And if you look at the other earlier equations and play around with those, you can show that the angle A, we'll use that as the controlling angle, that has to lie between 180 degrees over n minus 1 and 360 degrees over n. So for example, as shown here, n equals 5, A has to lie between 45 and 72. So here we show 8 different tilings. We start a little bit bigger than 45, and we end a little bit smaller than 72. So you can see the character changes quite a bit. The scaling factor is quite extreme at the start and gets closer to 1 as you continue. You might also notice that the eye, as you get into these skinny triangles on this end, very much wants to see 5 spirals counter-rotating, not 1 spiral clockwise rotating. And I'll come back to that. First, I just want to make the point that these tilings are self-dual. And in fact, if you choose any point in a triangle and keep that location consistent and then connect them, you get the same tiling. And there are 2 examples demonstrating that. So going back to the second set of spirals, all of these have a second set of spirals that counter-rotates, and there's more than 1 arm. So here we see, here's a counter-rotating spiral. There's a second one, and a third one, and a fourth one. Here there's 1, 2, 3, 4, 5, 6, 7. So the number of counter-rotating spirals is just given by n. Now, in addition to those types of spiral tilings, there are also spiral tilings which have more than 1 arm in each direction. So to derive equations for these, we have to modify our earlier equations. And here's the diagram. It turns out the first equation does not need to be changed. So if you scale 1, 2, 3, n times, you share an edge with a full size triangle, and you again write 1 equals bs plus as to the n. But notice this triangle is in a position here. If you rotate by the angle b to bring it up to where the hypotenuse is along the top. So it'll have gone through a 180-degree rotation. It's only half of a full revolution. And in fact, that the amount of a full revolution is just given by the number of arms. And so to modify the second equation, all we do is divide 360 degrees by m, where m is the number of arms in the tiling. And a now becomes this expression. So in addition to choosing c and n, we choose m and then calculate a and b, little a and b, and s, so that we can draw a tiling. Here's some examples with 3, 4, and 5 arms in the clockwise direction. In this case, n equals 2. So 1, 2, we share an edge. n equals 3. There are 3 different arms. The counter-rotating spirals, notice there's 2 starting in the yellow area, and here 2 start in red, and here 2 start in blue. So it turns out the number of counter-rotating spiral arms is just the product of m and n. So here n equals 2 and m equals 4, and in the last one, n is 3 and m is 5. There's an interesting special case when n equals m equals 2. In that case, you get these isosceles triangles with a 2-armed spiral like this. And this works for any angle. And the reason that's the case is because this patch is a parallelogram, and next generation is a parallelogram that shares 2 corners. And that kind of parallelogram construction works for any, any adjustment of the angles. So that'll continuously vary. And any patch of tiles that has a boundary that's a known tiling polygon can, of course, be used to tile the plane in periodic fashion. So here I've used those to create a tessellation with the color regions forming a sort of ram's horn shape. And if you do that a little bit differently and shift things, you can, with the same tiling, form this kind of curling S tile, tessellation. So there's another special case when a patch of tiles forms a regular polygon. If n equals 1, then regular m-gons admit m-armed spiral tilings for a continuous range of the angles A and B. So C is given by the polygon corner angle. And this is easy to see how this works. These have been known for a long time. I didn't know when they first came about. But you can just rotate your equilateral triangle inside a larger equilateral triangle so that you touch tangentially, and you'll get these sorts of spirals. This is a square case, so these are four-armed spirals. This is the isosceles triangle, and they get skinnier. These make quite attractive figures. For the triangle case only, you don't need a regular polygon. So if you have any general scaling triangle here, if you shrink it and rotate it, you can always touch at 3 points. That's not true for a general quadrilateral. So you can do this type of tiling for any general triangle, or isosceles, of course, or right triangles. Another thing you can do with these is do visual proofs. In this case, I took one of those tilings and I overlaid a kind of grid of 18 smaller triangles. You'll see that 12 are shaded and 6 are not. So the first generation covers 2/3 of the starting triangle. The next generation will cover 2/3 of the remaining 1/3. And you can write by inspection that the total area 1 is equal to 2/3 plus 2/3 of 1/3 plus 2/3 of 1/9. So it's a visual proof without words of an infinite series relationship. Here's another periodic tessellation using this type of tiling. After the first 5 generations, I just colored them all black, and I did some shading here to give a sort of illusion of depth to the design. And you can do an Escher-like tessellation, as Chirac showed, from any tiling. This is a frog and fish motif. The geometric template's pretty complicated. It's got 4 arms, and it's all the same right triangle, but it's actually appearing in 2 different orientations in this spiral. So in 2 arms, the hypotenuse faces out. Those I turned into frogs. In 2 arms, the hypotenuse faces in, and those were turned into fish. As another mathematical art example, you can do ring designs. To do these, I printed this tiling, physically printed it, and with a pencil, kind of just sketched circles that I thought might make good rings, each one encompassing a vertex. And then to refine that in a graphics program, I drew 1 circle on 1 triangle. I then scale and rotate that to form this kind of a drawing. And when you first try it, it doesn't quite work. The circles, maybe some of your gaps don't show, but you can move the circle a bit. You can adjust the diameter of the circle. You can adjust the thickness and find a ring kind of graphic that'll work. And then what you do is take a tile that's fully surrounded, so it's penetrated by all the other circles, like this one. And then I rendered that in a sort of over-under weave pattern. And so every tile then is going to be identical to this, except that on one half I flip the colors. And what that looks like when you put it together and drop out the triangles is this. So by using a triangle tiling, I made a quite complex ring design with relative ease. Okay, I've got a few minutes. So I've started looking at quadrilateral tilings. I've not explored all the possibilities. This sort of tiling, which Chirac talked about, has been known for a while. I'm not sure exactly when it was first discovered, but in this case, you have multiple arms and they're edge to edge. But I was interested in looking at something more like what I was doing with the triangles. And so we do a drawing like that and label things. It's a little harder in this case. So we have sides A, B, C, and D is 1. A, B, C, and D are the angles. We scale and rotate, arrange the base on the side here. And after n rotations, we're over here where we're sharing part of an edge. And one more rotation shares another edge of the quadrilateral. So your equation now is 1 equals bs plus cs to the n plus as to the n plus 1. And you can again write an angle relationship. And that's not enough to solve it though. You can't just choose c and n and be okay. What you get is a and should be b plus d. So the further step that's needed is, the way I did this was to draw a diagonal p to divide the quadrilateral in half. And then I just chose a value for d1 between 0 and d. And that gives you a1, a1 gives you a2, gives you d2, and then you just work back and solve everything. And you can do accurate quadrilateral spirals then. Here's another example, n equals 4. So 1, 2, 3, 4, you're touching on an edge. There's your angle, scaling factor is about 85%. And Cy Waldman also found this independently about the same time using a somewhat different method. He and I have both been looking at spiral tilings in recent years. So finally, I have to plug my book. This came out about 8 months ago by CRC Press. It's about 450 pages. It's full color throughout. Lots of background, chapters on geometric tilings of various sorts, including spirals and fractal tilings. It's also got several chapters on how to design your own Escher-like tessellations. And it's got nets of polyhedra in the back with tessellations applied to them. You print and build tessellated polyhedra or design your own tessellated polyhedra. Each chapter has some classroom worksheets. There's a lot of stuff in there. I hope you'll check it out. You can buy it at major booksellers like Amazon. You can also buy it from me. If you buy it at Math Art Fun, I'll send you an autographed copy for what that's worth. And that's it. Here's my email. That's my art website, Facebook and Twitter handles. A lot of my recreational math is on fractaldiversions.com. Unfortunately, the stuff I just talked about is not on there yet, but it's on my social media stuff. And this is a website for the book. So thank you for your attention.